Alright, so we're going to take a look at differentials. Go ahead and fill out your last tab. So this is the last application for derivatives that we're going to look at before we move on to the next chapter. Alright, so differentials is a small quantity that corresponds to a change in the number. And we're going to represent it as a change in x basically. It is used to find the error of approximation or to approximate a function. Right, so it can be used for two things, to find the error of the approximation or to actually approximate the function. Alright, so do you remember the original formula for derivative? It was f prime of x as the limit as h approaches 0 of f of x plus h minus f of x all over h, right? So let's replace h with a change in x and get rid of the limit. So now we're going to get an approximation of the derivative. The listening check, color in this sentence. So we're going to get the derivative of f of x is approximately, and you do that by that little curve on the top of the equal sign. Right, f of x plus, now instead of h you're going to put change in x, minus f of x all over, and instead of h you're going to put change of x again. Alright, now you're going to solve for f of x plus the change in x, the differential. Alright, so we're going to multiply both sides by a change in x, and then we're going to take the negative f of x to the other side, leaving what I want by itself. So change in x, derivative of f of x plus f of x is approximately equal to f of x plus change in x. I'm just going to rewrite it in the way you're going to see it, which is basically f of x plus change in x goes first, and then f of x plus the change in x times the derivative. So this is now the formula for differentials. So the small quantity that represents the change in a number. Okay, the value of a function, this is all it says. The value of a function, right, at x plus a little bit. This is a listening check, put a box around formula for differentials. Is approximately equal. And I always forget to do that. It's approximately equal. It's not exactly equal. It's approximately equal to the value of the function at x, right? That's f of x, plus the product, because now you're going to multiply the two things together, the product of the derivative of the function at x with a little bit. Alright, so I just basically put this in words. Let's take a look at an example. So it'll say use differentials to approximate the square root of 9.01. So listening check, color in example 1. Alright, so you start off with determine what the function is. Over here it's the square root of a number. So I'm going to write that down. F of x is the square root of a number. Let's call that number x. Alright, let x be equal to like the closest thing, the inside of a function of what you know. So for example, in this case, I don't know the square root of 9.01, but I know something really close. I know the square root of 9. So let x equals 9. And then the change in x is going to be that little bit that I don't know. So it's the change in x is going to be adding 0.01 to it because I really want the square root of 9.01. So let the little bit equal the change in x. So that's 0.01. I don't know why I write 0.1. I think I'll fix it later. Right, number 4, find the derivative of the function, because I'm basically looking for everything in this formula. So the derivative of the square root of x is going to be 1/2, because it's x to the 1/2. 1/2 x to the negative 1/2, and rewriting that 1 over 2 radical x. Right, so now I'm just going to plug everything into the formula. Okay, so plug into the formula. So the formula says the function of x plus a little bit is approximately equal to the function of x. This is a listening check. Put a box around the formula that we're writing, plus the product of the change of x and the derivative of that function at x. Alright, so let's plug some stuff in. So f of 9.01 is approximately equal to the square root of 9 plus 0.001, which is a change in x. So I go ahead and fix that. Over the derivative, which is 1 over 2 times the square root of, and what's x? 9. Alright, so what's that? So that's approximately equal to 3 plus 0.01 and then square root of 9 is 3, so 3 times 2 is 6. And then you're just going to plug that in the calculator. So type in that in the calculator. I'm going to get 3.0016666667. Now, this is just an approximation. So now I'm actually going to type in what is the square root of 9.01 right into the calculator. And when I do that, I'm going to get 3.0016666204. So you see, I'm going to color what they have in common. See, so they have quite a lot of numbers in common. So this approximation is pretty close. So the question could come up, what is pretty close? Like, what's really close to 9.01? Well, let's take a look at another example so that I can show you something. So use differential to approximate the square root of 9.5. So same thing as before, f of x is the square root of x. X is 9. The little bit, the change is plus 0.5. We need the derivative, so we can plug it into the formula, which is the same thing as the one before. Okay, and I always write this out because I forget the formula, so I always do it from scratch, and this will be good practice, so make sure you do it. So remember the original derivative, replace h with change in x and get rid of the limit, and that's an approximation. Solve for f of x plus the change in x, so multiply both sides by the change in x. And do this every single time because it's a way for you to memorize the formula, because I never remember it. You know me already, I don't remember it. Alright, then move that to the other side, and that's what your formula is. Alright, so the function of 9.5 is equal to the square root of 9 plus the change in x, so 0.5, times the derivative of that function. So 1 over 2 square root of 9 again. Alright, so that's approximately equal to 3 plus 0.5 over 6. Because this time my change is 0.5. Alright, so plug that into the calculator. You're going to get 3.083 repeated. Alright, what is actually the square root of 9.5 in the calculator? You're going to get 3.08, and then it changes to 2207001. So you can see that my change in x was a little bigger, it was less accurate. So this is what it says: as the ratio of the change in x over x grows larger, the approximation gets less accurate. This is a listening check. Color in this sentence that we're writing right now. There is a formula that is used to estimate the error in measurement, or this error in measurement. And this formula is really easy to remember. It's dy equals the derivative of that function dx. And dx is the differential. Alright, so the change in measurement dy, I'm just going to write in words, due to a differential dx is found by multiplying the derivative of the equation for y by the differential. So again, the dx is the differential, which represents a small change in quantity. So let's take a look at an example doing this. The radius of a circle is increased from 3 to 3.04. Estimate the change in the area. Alright, what are we talking about here? We're talking about area, and we have a circle. So what's the area of a circle? Pi r squared. So using the formula that we just got, I'm just going to rewrite it in terms of area. The change of the area is going to be equal to the derivative of the area times the differential. So where a prime is the derivative of the area with respect to the radius. As a listening check, color in area is pi r squared. And dr, which is the differential, is 0.04 because that's how it changes. Alright, so remember dr is just the differential, the small change we're talking about. So it changes from 3 to 3.04, so the small change is 0.04. Alright, so take the derivative of area, you're going to get that, and then plug it in. So dA is equal to the derivative, which is 2 pi, and what's the radius? 3, times the small difference, okay, which the differential is 0.04, and plug it into the calculator. So you're going to get 0.7539822.369. Now, what's the actual change in the area? So the actual change in the area is what it becomes minus what it originally started off with. So when the radius is 3, the area is 3 squared, which is 9, so 9 pi. When the area is 3.04, the area is the radius squared, which is 3.05 squared times pi. And I'm just gonna plug it in the calculator. So the change is gonna be the difference between those two. So the difference, what it ends up with, which is 3.04 times 3.04 times pi. And then you're gonna subtract what it started off with, which is 9 pi. So 0.7590087851. So I'm just gonna color in the common numbers. So 0.75. And that's pretty close, to be honest. That's pretty close. Let's take a look at one more example. The radius of a sphere is measured to be 4 centimeters with an error of plus or minus 0.01 centimeters. Use differentials to approximate the error in surface area. So start off with the surface area of a sphere, because that's what we're talking about. Surface area of a sphere is 4 pi r squared. And you have to remember these formulas, you have to memorize them. Alright, so we're going to need to take the derivative, or I can write it out in terms of the surface area. But take the derivative of surface area, which is going to be 2 times 4 is 8 pi r. And then I'm going to write the formula out in terms of the things I'm using, which is the change in surface area, so let's call that ds, is the derivative of the surface area, derivative of s, and to multiply by the small differential. So what does that give us? The change is equal to the derivative of the surface area, which is 8 pi times 4, which is the radius, times the small change, which is 0.001, which is equal to plus or minus 1.00530969. Let's take a look at what the actual surface area would be. So the actual surface area would have been 4 times pi times r squared, which is, what's 4 squared is 16. So plugging that in, we're going to get 201.061. And that's a really big number. So given that the actual surface area is that number, then this plus or minus 1.0053 error is really quite small. Okay, so one final thing that you need to remember, note when you're approximating trig functions, you must use radians. When you're approximating trig functions, you must use radians. Do not use degrees. You must use radians. You must use radians. You must use radians. Okay, not degrees. This is generally true. I forgot to write the word true, so that's a listening check. Write true. This is generally true for everything in calculus. And that's pretty much it for differentials, so let's practice.